So let's go ahead and let's look at the details of what is required to actually get a chemical reaction to occur, and basically how that's connected to our chemical kinetics studies so far. So we've already talked about the four factors that are going to affect reaction rates. We've talked about concentration of reactants, and basically from our rate laws that we just looked at, we know that if we're increasing our concentrations, we increase our rates. It's pretty straightforward. We're going to look at the nature of our reactions, our temperature, and catalysts is something that we're actually going to look at a little bit later. But we want to take a little time to refresh as well as emphasize a few points in these four factors. Okay, so we're going to skip number one as concentration is obviously going to affect the rate of our reaction, and move straight on to number two. So basically the nature of the reactants, what we're referring to is basically the specific features associated with specific reactants are going to affect the type of reaction that you end up with. Okay, so an example series that we've already looked at in previous lectures is basically the reaction of the alkali metals and alkaline earth metals with water. Okay, and we know that sodium reacts very vigorously with water at room temperature, and in that process it liberates both hydrogen gas and produces sodium hydroxide base. So we studied this a little while ago, so basically a rehash there. In that same thought process, or the same reaction type, we have calcium reacting with water. Okay, and we know that this process occurs very slowly at room temperature to release the hydrogen and metal hydroxide that would be expected. Now, these reactions are both occurring between metals and water, okay, and they are both producing hydrogen gas and a metal hydroxide salt. So really, what is the difference between these two reactions? Well, obviously, it's the type of reactant metal that is used. Okay, so alkaline metals such as sodium and the lot in its group, okay, behave in specific ways, versus calcium, okay, it's an alkaline earth metal, behaves differently because of its features, and that has to do with, remember, valence electrons and how far away they are from its nearest noble gas, and things of that sort. So remember that your rate of reaction is going to be dictated by features specific to your reactant types. Okay, so chemical reactions, they do speed up when temperature increases, and this is because K is dependent on your temperature. So a great example of this process is basically glow sticks. We can put them into a cooler reaction mixture, so basically room temperature or below, and we can also heat up the reaction container in which the glow stick is placed in, and as you can see, there's a distinct difference in terms of the brightness of the glow, which is indicative of an increase in the production of the chemical that causes the glow sticks to actually glow. Okay, so we know that if we increase our temperature with the vast majority of reactions, we are going to have an increase in the rate of that reaction. Okay, so now that we've looked at a few additional details of our factors that are required for reactions to occur, we want to look at this collision model and basically why there are some discrepancies in terms of what you would expect to happen in terms of, basically molecules bumping into each other, so we should get reactions all the times. So remember, molecules must collide to react, and basically kinetic molecular theory, or the idea that molecules are always in motion, is connected to the idea that if we increase our temperature, we increase our speed of those molecules, and if we increase the speed of the molecules, we increase the frequency of those collisions. Okay, but what we actually end up seeing with respect to the actual reactions is that the rate of reaction is usually smaller than the calculated collision frequency. Okay, and there's two factors that affect the effectiveness of our collisions. Okay, so the small fraction of collisions that actually produce a reaction need to fulfill two requirements, and we've talked about these before. Basically, you need the appropriate amount of kinetic energy, and the molecules must be in the correct orientation. Okay, and so we're going to kind of expand upon the energy component of the collision model and look at something called activation energy. Okay, so your activation energy, or E sub A, is the energy that you must have, or that you must put into a system in order to get your reactants to go into their product form. Okay, so if we look at these graphs down here, okay, notice we have our reactants here, we have our products over here on this side. Okay, so in order to go from this reactant into our appropriate products, we must add a specific amount of energy. The energy difference between our reactant starting energy value and the component that's known as a transition state, which we'll talk about here in a minute, okay, is that energy that must be overcome in order to get the collision to give us a reaction. Okay, so your activation energy is represented here and must be overcome in order to get those reactions to occur. Also, in that same thought process, in that transition state, the molecules must be aligned properly. In this case, we want bromines to interact with each other. So in this case, the bromine and bromine atoms in the two molecules must align in a way that they can actually interact and subsequently give us the Br2 product that we anticipate. Okay, so let's continue to look at this activation energy and this energy progression diagram that we have here. Okay, so we have our energy, we have our reaction pathway, okay, we have our reactants, we have our products. Okay, so what ends up happening is basically energy must be added to a reaction, okay, or there must be enough energy in a reaction in order for this activated complex or transition state to be met. Okay, so once this transition state is met, okay, then you can actually proceed into your products. Okay, so your activation energy is going to be the measure of the energy between the activated complex, or basically the top of the hill in terms of the energetics needed for your chemical reaction to occur, and the original energy value of your reaction. Now, your activation energy, guys, is going to generally dictate rate. So the bigger your activation energy, the slower your reaction is going to be. Why? Because more energy must be achieved in order to get to the activated complex and then subsequently move into our products. So basically, activation energy, guys, is going to dictate your rate. The bigger it is, the slower your rate. The smaller it is, the faster your rate. Okay, so also with the collision model, we want to pay attention to these orientations. We've just talked about our activation energy. We need to overcome that. In that same way, we must overcome any abnormal interactions between, or not abnormal, but ineffective interactions between the molecules. Okay, so A and B are both examples based on the previous reaction that allow us to see an appropriate interaction between the molecules needed in order to produce the appropriate products, which in this case is the Br2 and the Br2 and the NO2 and NO2. Okay, if the molecules interact in this direction where the oxygen atoms are coming into proximity, there's not going to be a way for those bromines to interact and subsequently give you the products that you desire. So instead, basically they'll bounce off each other and then float around and hopefully bump into something else with the correct orientation and correct energy and subsequently give you a reaction. So the collision model basically needs to fulfill the two requirements that we've already discussed. Okay, basically the appropriate energy as well as the appropriate orientation. Okay, and now we've introduced activation energy, and that activation energy is going to connect us to our next component, which is known as the Arrhenius equation. Okay, so Arrhenius basically noticed that for most reactions, the rate of your reaction increased with temperature. Okay, so basically, anytime we're increasing our temperature, we should see an increase in that K value. Okay, and that led him to basically establishing this equation. K is your rate constant. A is actually a frequency factor. Okay, EA is your activation energy, that energy we just talked about in the previous slides. R is your gas constant with these units. Okay, and T is your temperature with respect to Kelvin. Okay, so what is frequency factor? Okay, well, this frequency factor is basically the probability of your collisions having sufficient energy and orientation in order to actually give you a reaction. So really, what we have here is a relationship between our activation energy, our temperature, and the rate of our reactions. Okay, so, and if we look at the equation here, basically, if we increase our activation energy, the value of K, or the rate of our reaction is going to decrease, and that's supported by the observations that most reactions that require large quantities of energy are obviously going to be less likely to occur. Okay, so how could this type of information from the Arrhenius equation help us out with respect to understanding the likelihood or rates of generic reactions? Okay, so we have reaction progression graphs here for reaction 1, 2, and 3. Okay, and basically we can establish which one of these reactions has the fastest or slowest rate based on the activation energy values provided. Okay, so the EA, the activation energy, remember, is the difference between the energy and the reactant of your products up to that transition state, right? So in this case, it's 15 kilojoules per mole. In this case, it's 25 kilojoules per mole, okay? And in this case right here, it's 20 kilojoules per mole. Notice reactants versus that peak where the transition state will occur. Okay, so remember we talked about that the bigger the EA, the slower your reaction is going to be. Okay, so in this situation, reaction number 2 has the largest EA. So by default, if it has a bigger EA, it's going to have a slower reaction. So if we're ordering these in order from slowest to fastest, we know for sure that the slowest reaction is going to be reaction number 2, okay? And based on the same concept, we know that our fastest reaction is going to be reaction number 1, okay? And obviously reaction number 3 is in between, so that's the progression. So from slow to fast will be basically related to our activation energy. The bigger the activation energy, the slower your reaction. Okay, so we can also use the Arrhenius equation in order to solve for activation energy. Okay, and basically through some manipulation of this equation, basically taking the natural log and doing some rearrangements, we can get this equation, which is very commonly used graphically. Okay, so what we'll do is we'll look at this equation as basically a line equation here, where y is equal to ln of k, m is equal to negative EA over r, okay, x is equal to 1 over t, and obviously our b value is going to be ln of a. So basically what we can do is we can take and graph our y and x components and subsequently get the slope of the line that's produced from that data. Okay, and if we get the slope of the line, right, we know that the slope of the line is going to be equal to the relationship between our activation energy and our gas constant. And then we can subsequently take that information and solve for our activation energy for that specific progression. So basically we can know our rates and our temperatures, do some graphing, and basically plug them in appropriately and subsequently get our reaction activation energy. Okay, so we have, the modified and rearranged Arrhenius equation here. Okay, and the reaction that we're looking at is basically this decomposition of dinitrogen pentoxide. And what ends up happening here is we've actually studied it at various temperatures. Notice it's not at a constant temperature, it's at different temperatures, and we got the various rates associated with each of those temperatures. And we would expect, obviously, a change in rate as we basically monitor the progression of the reaction. So, the higher our temperature, we would expect a faster rate, which is what we see here. So what we do is we take this information, okay, and we graph it. So we take K and basically plug it into ln, take the natural log of each of these, okay, and that's going to go into our y data for our graph, okay, and then we take our temperature, we convert these to Kelvin and take basically inverse of it, okay, so 1 over each of the Kelvin temperatures, and we graph those, and we'll basically get a straight line. We then take that straight line and we find the slope of the line. Okay, we take the slope of the line, we do that rise over run type of thing, and we subsequently calculate that slope. So once we've established that, we know that the slope of the line, the numerical values that we get from the slope off of this actual line in the graph, is going to be equal to negative EA divided by R. Okay, so then what we do is basically rearrange the equation. So our negative 1.2 times 10 to the 4 K is going to be equal to negative EA over 8.314 joule per mole Kelvin. Excuse me. Okay, once we do that, we're then going to cross multiply up and divide out by the negatives. Okay, and that's subsequently going to give us EA equal to 1.0 times 10 to the 5th joules per mole. Okay, so basically we've been able to establish the rates at various temperatures. Okay, we've taken those values and appropriately adjusted them, basically taking the natural log of our K's, converting our temperature to Kelvin, and dividing each of those into 1, and subsequently graphing that data. We graph that data, we subsequently got the slope of the line. We know that the slope of the line is equal to negative EA over R, okay, and we know R is our constant, so we can plug in that value and subsequently solve for our EA, which is seen here. So the Arrhenius equation can also be exhibited in two-point form. So basically, we can use this equation here to calculate the activation energy from K values at 2 specific temperature. So basically, this equation right here is obtained through the rearranging of the subtraction of ln of K1 and ln of K2. We don't really need to know how to go about doing that. Just memorize the equation and it'll save you a lot of time. So let's go ahead and apply the usage of this equation. So we're going to go ahead and utilize the two-point form of the Arrhenius equation in order to solve this following problem. Okay, so we're going to be using this. In order to calculate our activation energy for this specific reaction. So basically the rearrangement of cyclopropane at these 2 different temperatures. Okay, so we do know we're going to be using temperatures. These are going to need to be in Kelvin. 573 Kelvin and 623 Kelvin. Okay, we have our 2 rate constants. Okay, this is going to be K1, this is going to be K2, T1, T2. And we're going to subsequently plug them into the equation. Okay, so ln of 2.4 times 10 to the negative 10 divided by 2.3 times 10 to the negative 8th. Okay, that's going to be equal to EA over R times 1 over T2, which is 623 Kelvin, minus 1 over 573. And basically, we're going to plug our values into our calculator. If you want, you can do your rearrangement first. Okay, so we could do ln of 2.4 times 10 to the negative 10 over 2.3 times 10 to the negative 10, negative 8, I apologize. Okay, divided by 1 over 623 minus 1 over 573, all times our R value, okay, and that will give us EA. Okay, so if we go ahead and plug this into our calculator, which is this math here times 8.314, okay, that is going to give us an activation energy equal to the following. Okay, now they want the answer in kilojoules per mole, so basically we need to make an additional conversion, basically removing that decimal, those three spaces, so 271 kilojoules per mole. Okay, so basically in this situation we can utilize the Arrhenius equation in two different forms. The two-point form basically allows us to compare temperature and rate constants of specifically analyzed reactions to solve our activation energy, or we can use our graphical approach that we did previously in order to take advantage of calculating the activation energy from the Arrhenius equation.